Now we want to start graphing some functions using implicit differentiation. So the first one we want to look at is x squared minus y squared is equal to 4. Now there's what our graph's going to look like. So again, this one we could probably do through explicit differentiation, but we'll see the process and what happens. So what do we need to establish? Like, we need to establish critical points, stationary points, if there are. And so we're looking here first at, well, what are critical points? Well, let's have a look where it goes through the axis. So if we've got x squared minus y squared is equal to 4, when x is equal to 0, then you get 0 equals minus 4 squared equal to 4. So that gets us y squared is equal to minus 4, which is undefined. So there's no y-intercepts in this case. So we don't ever go through the y-axis. So, well, and that's the case because x squared minus y squared, well, there's no values there we can make that equal to 4, where that will be less than that. So, because it's always subtracting y squared, so you can see why that's going to be the case. It also starts to establish, you can also establish that your domain is going to be greater than 2 and less than minus 2, because the smallest value of y is going to be 0. And so you're going to have that going to be a situation, well, what's the value of x when in that case, and there's your 2 and the minus 2, which we happen to have for our intercepts there. So we're going to have a situation where that's going to be greater than, because x is going to be having to be greater than 2 or minus 2 when we're going to get this to work. So, other critical points. Well, let's have a look at what we're getting for our stationary points. There's our establishing our values for the domain. There's that mathematics there. So we look at our gradient function. So again, implicit differentiation gives us the 2x minus 2y dy dx. Solving for dy dx gives us x on y. Now, and we know x can't equal 0, so dy dx can't equal 0 either. So that means we're not going to get any stationary points, because only the numerator can be 0. We've already established that x is less than minus 2 or greater than minus 2. So no stationary points are going to exist on this one. But also what we can see though is that when y is equal to 0, so if we have a situation when y is equal to 0, dy dx becomes undefined because we get a division by 0, which means for our derivative, and we get vertical tangents at that point. So y is equal to 0, minus 2 minus 2 0 2 0, which we had before. We're going to get vertical tangents there. So that's what we're going to be able to look at and go, okay, well, what happens with that equation? So what we can see our vertical tangents occurring there at 2 and minus 2. X is greater than, always going to be greater than 2. Y is going to be greater than, x is going to be less than minus 2. So we can start looking at what happens as x approaches infinity. So it's going to approach, you can start to see that they're going to get closer again. As x gets larger, y is going to have to be larger, because their difference is always going to be 4. So even though it turns, it starts to look like it's going to go on that line y is equal to x, because they're going to be so close together. Y and x are going to be very close the further you go, because again, the difference is only 4. The larger they get, and they're squaring to give you a difference of 4. So you can start to see where the arms of those, and this is a hyperbola, start to come into play and what they start to look like. So we could definitely draw an asymptote of y is equal to x, and so y is equal to minus x and y is equal to x, and that's where it's going to go in this case. So there's the first one. So again, we get those critical points, where it goes through the axis, what the gradients are doing. Have we got stationary points, or in this case vertical tangents that exist to draw our graph? So the next one, x to the power of 3 on 2 plus y to the power of 3 on 2 is equal to 1. So it comes from this situation, the square root of x cubed. Again, what's our domain and range? Well, because it's going to be equal to 1, and they're always going to be equal to 1, adding, x is going to be greater than 0, because you can't take the square root of a negative. So it's going to be positive there, and the same with y, which means that x is going to be has to be between 0 and 1, because if x can't be greater than 1, because we take the square root of anything else there, it's going to give us something greater than 1 there, and the 2 have got to add to it, and y is equal to 1, it's got to be between 0 and 1 as well, which means that if x is equal to 0, y is 1, and y is equal to 0, x is 1. So there's some critical points. There's our domain. So what's happening for our gradients? Well, we can get our derivative, so we derive this function implicitly, the 3 on 2 x to the power of a half plus 3 on 2 y to the power of a half dy dx is equal to 0. So again, we've played around with it and gone minus half x to the power of a half and divide by y to the power of a half. So what's happening here? Well, it's going to, because we can only take x and y being positive, we've got the negative here, which means the gradient's always going to fall. It's always going to be decreasing. And well, for it to have a stationary point, well, the whole thing would be equal to 0. So only x can equal 0. So it's got to, when x is equal to 0, we've got a stationary point. And when y is equal to 0, it's going to be undefined. So we've got a vertical tangent. So we'll put that all together. And as I said, it's only going in the first quadrant. It's going through those points. The gradient's always falling. Stationary at x is equal to 0, y is equal to 1. And has a vertical tangent when x is equal to 1 and y is equal to 0. So what does our function look like? Well, it looks like that. So first quadrant, stationary here, vertical here, always falling. So that's how we're able to get our graph of that function. So you can start to see, looking for domains and ranges. What's our restrictions on our x and y's? That's going to help graph our function. What are the critical points? Are they going through the axes? So are we going to get that? And then we'll let him look at the gradient of the function. What's happening there to the function as you go through the critical points, and between the critical points, can we make some sort of judgment in that? So there's a couple of examples of implicit differentiation, how that helps us to graph a function. Like, try to put that in explicitly would be really difficult in trying to get the function there. So implicit differentiation starts to make life a little bit easier. They're not easy functions to start off with, but hopefully we can start to make it a little bit easier to graph functions in these forms.